The Earth is surrounded by an envelope of air, known as the atmosphere. Although the atmosphere is about 1,500 miles deep, at present most of the flying is done in a layer about 10 miles thick. Air is very light. A sample of it may be represented like this. If we pile samples one upon another, the air at the bottom is compressed and its density is increased. The atmosphere can be thought of as many such columns of air, which form layers, dense at the bottom and thinning gradually as we go higher. This variation in density or pressure with height can be demonstrated with a balloon. As it rises, it enters a lower atmospheric pressure and therefore expands. When the balloon moves horizontally, the volume remains the same. If the balloon is replaced by a sealed empty can, this also will expand as it is moved up and contract as it is moved down. These variations in pressure can be measured by fixing a pointer to one side of the can. By adding a scale calibrated in millibars, we can obtain pressure readings. At 5,000 feet, the pressure is about 850 millibars. As we descend, the pressure increases. Near the ground, it is about 1,000 millibars. Ascent causes a decrease in pressure. At 10,000 feet, it is about 700 millibars. We have thus obtained a series of pressure readings. Pressure, it seems, is related to height. It looks as though we can change our instrument to a height indicator by merely changing our pressure scale to a height scale. This we could do if the pressure-height relationship of the atmosphere were always constant, that is, if its density remained uniform. Unfortunately, we do not always find the same density at the same height. The pressure pattern is continually changing. The pressure layers rise and fall according to the amount of atmosphere above them. An increase in the amount produces a dip. A decrease in pressure causes the layers to move upward. Horizontal movement of our instrument through this atmosphere causes a change in pressure readings. Notice that the height of the instrument is constant. Only the pressure layers are varying. Let us now hold the instrument at a constant pressure of 850 millibars. Since we are now following the pressure layers, we obtain a series of height readings. To convert the instrument to a height indicator, we must decide which height is to go on the scale. An answer to this important question had to be found before a practical height indicator could be developed for aircraft. The solution was found by making the instrument behave as if it were in an assumed constant atmosphere. In this atmosphere, the pressure-height relationship never varies. The sea level pressure of the atmosphere is taken to be 1,013.2 millibars. The 900 millibar level is at 3,200 feet, and the 800 millibar level at 6,400 feet. To each pressure is assigned a definite height. This assumed constant atmosphere is representative of the average atmospheric conditions found in many parts of the world. It is known as the ICAO standard atmosphere. Here is our pressure instrument. We can now convert it to a height indicator. All aircraft altimeters are calibrated in this way. They thus provide consistent height indications for any given pressure. A pilot requires 3 distinct types of indication from his altimeter. First, he wishes to know his altitude, that is, his vertical distance above mean sea level. The elevation of mountains and other obstacles shown on his chart is measured from mean sea level. So by subtracting this elevation from his altitude, he can determine his distance above the terrain. In some areas, he may be required to fly on flight levels. These surfaces of constant atmospheric pressure are spaced 500 feet apart. Flight level 0 is at the 1,013.2 millibar level. Above it, the levels are identified by numbers. Short numbers are used instead of the actual altimeter indications to distinguish heights from altitudes when reporting. When landing, the pilot may wish to know his height above the aerodrome, since landing charts indicate the height of obstacles in the vicinity of the aerodrome. Let us now see how the pilot obtains these 3 indications from his altimeter. The altimeter is provided with an adjustable pressure scale. If it is set to 1,013.2, the altimeter will indicate 0 height at flight level 0. This is because 1,013.2 is the pressure at flight level 0. If the altimeter is raised to flight level 50, it will sense a pressure of 843 millibars and will indicate a vertical distance of 5,000 feet above flight level 0. If the altimeter indication is kept constant, the flight level will be maintained. The altimeter is, of course, following a pressure surface. As we have seen, the pressure levels are continually changing. When they dip down, the flight levels descend. This is what happens when flying into a low-pressure area, or cyclone. When flying into a high-pressure area, or anticyclone, the pressure surfaces bulge upward. But no matter whether the pressure surfaces move up or down, the vertical distance between flight levels remains the same. Different flight levels can therefore be used to provide separation between aircraft. While flying on a flight level, the pilot may wish to know his height above the terrain. To determine this, he must first find his altitude, that is, his vertical distance above mean sea level. Since he is flying on a flight level, his altimeter subscale is set to 1013.2. The altimeter is therefore measuring the vertical distance above the 1013.2 millibar level. Since his instrument is calibrated to the standard atmosphere, it will sense a pressure of 843 millibars at flight level 50. His altimeter therefore indicates 5,000 feet above the 1013.2 millibar level. The pilot, however, wants to know his height above mean sea level. To determine this, he must find the pressure at this level. This pressure must be measured by an observer on the ground. The pilot, therefore, radios the nearest ground station and asks to be supplied with this information. At the ground station, an observer computes this mean sea level pressure. For example, he may find that it is 1,030 millibars. This pressure reading is called a QNH. It is radioed back to the pilot, who resets his altimeter to the QNH setting. In doing this, he has dropped the height scale so that 0 corresponds to 1,030 millibars. At flight level 50, where the pressure is still 843 millibars, the altimeter now indicates 5,447 feet, this time above mean sea level. The pilot can now subtract the elevation of the terrain from his altitude and obtain his terrain clearance. Landing charts show the height of obstacles in the vicinity of the aerodrome. A pilot making a landing may wish to have his altimeter indicate the height above the aerodrome. Remember that if the altimeter is set to 1013.2 millibars, it measures the vertical distance above the 1013.2 level. At flight level 50, where the pressure is 843 millibars, it will indicate 5,000 feet. In this case, however, the pilot wishes to know his vertical distance above the aerodrome level. He must, therefore, find out what the pressure is at this level. As before, he obtains this pressure setting from an observer at the aerodrome. In this instance, it is 933 millibars. This pressure setting, called a QFE, is transmitted to the aircraft. As before, the pilot adjusts the pressure scale on his altimeter. In doing this, he has moved the 0 of the height scale to 933 millibars. 2,735 feet is now the altimeter indication at flight level 50. This is the height above the aerodrome level. The height of obstacles shown on the landing charts can now be compared with the altimeter indication. The altimeter will indicate 0 height on landing. To summarize, a pilot uses three distinct types of altimeter indications. When a setting of 1013.2 millibars is used, the altimeter indicates vertical distance above this pressure level, that is, flight level 0, and the pilot can determine the position of any flight level. When a QNH setting is used, his instrument measures vertical distance above mean sea level, that is, altitude. When a QFE setting is used, it measures height above an aerodrome runway. We thus have this simple relationship between the pressure setting and the altimeter indication. 1013.2 millibars gives flight levels. A QNH setting gives altitude. A QFE setting gives height above the runway. These terms are not interchangeable. They must always be used in their correct sense.